I'm grateful in particular to the Garage for inviting me here and giving me this opportunity to speak today. And it was actually my severe disappointment at being forced to miss Scala B last year that, there was a scheduling conflict with another conference, and it actually inspired me to create a spreadsheet for all the Scala conference organizers worldwide to make sure it would never happen again that I would miss a conference like Scala B. And I can confirm that Scala Swarm is the only Scala conference going on right now, and hence, here I am. And I don't like to miss an opportunity. So this picture here is a scene from the venue for my conference, Scala World. I won't. Some of you here maybe like conferences, perhaps. We're having this event in September, so I'm not going to miss the opportunity to sell to a captive audience. But if you're interested in extracurricular activities like hiking, canoeing, then in a location like this, then have a look at scala.world, the website, and I will quit my sales pitch there. Could we take the volume down a little bit on my voice? Is that okay? I'll leave the photo there so you can enjoy it. So it's not often I get the opportunity to present this sort of talk, and it's given me a chance to talk about a topic which is absolutely fundamental to my career as a programmer. And I generally prefer understatement to exaggeration. But I truly believe that this is something that has made my work as a software developer more pleasant, more enjoyable, and actually measurably improved my life, my entire life. And I'm talking about types, the Scala type system specifically. Now, I started my career in 2004 as a Java programmer. I only lasted a few months as a Java programmer, but I did some stuff in Java. I don't look back fondly. And it was actually pre-generics Java. It was Java 1.4, so I never actually wrote any generics in Java. But I remember painfully, that much of the work I was doing back in 2004 in Java was putting values into hash maps. And then sometime later, I would take them out of those hash maps again, and I would cast them. I would cast them into some other type and hope that it was the right type. And I remember a particularly unpleasant experience where I was trying to represent some sort of tree-like structure using values stored recursively into hash maps. And it was thoroughly unpleasant because I couldn't get it working. Now, this is me as a 20-something-year-old programmer with not a huge amount of experience, and the code I was writing was probably very sloppy. It wasn't easily unit testable. That didn't really matter because I wouldn't have written the tests anyway, but I had low coding standards. But the experience and memory of writing that code, those hash maps, and all those casts, I look back and I think how horrendously awful that was. How painful my life was back then when I was having to do that. Debugging was difficult, and it seemed like the amount of code in my project was so much larger than, just so much disproportionate code compared to the complexity of the problem I was trying to solve. And I'm sure you've all been in those situations where the complexity of your solution seems disproportionately greater than the perceived complexity of the problem. And you feel like you're fighting unnecessary battles all the time, just to make it work. And it was in this context, in the autumn of 2004, that I discovered and started using Scala. And I don't know, but there's probably nobody here who remembers Scala 1. Any takers? No. So you'll have to appreciate that the type system in Scala 1 was not the same type system we have today. It was still an order of magnitude better than the one I was familiar with in Java. But And I found myself able to write the same functionality in fewer lines of code, and crucially, with fewer casts. And I think unlike most Scala programmers today who have been more or less handed a complete type system, a complete, mostly working type system with only a couple of unusual soundless holes, I developed my understanding of Scala's type system very much as the features were being added, as the type system was developing. And I was able to remove, slowly, year by year, many of those casts from the code. The compiler was slowly getting better and better. It would be interesting, actually, to have run an experiment where I tried to migrate the same code from 2004 in Scala 1.3 up to Scala 2.12, and to count the number of occasions where I needed to use casts back then compared to now. I never had such a project and never did the test, but it would be interesting to have tried. But the progress has been steady. It's been continual and steady. So it's been, I think Marco said, almost a decade. It's actually been 13 years, nearly, I've been using Scala. And what have I achieved? I've removed some casts. So, yeah, big deal. So to most people, this wouldn't sound particularly impressive. Maybe to everybody, it doesn't sound particularly impressive. I mean, it's very satisfying, but it takes some explanation before you can appreciate the value in having removed those as instance of calls. Because a cast, a call to as instance of, seems very much like a failing of a programmer. It's the programmer claiming to the compiler that despite everything the compiler knows about the universe, the programmer is saying, I know better than you do. I know something which means that I feel it's safe to make this cast here. And this means one of two things. Either the compiler is deficient in some way. Either the compiler is unable to deal with this information and use the knowledge it's given, or the programmer has failed to express this information in the language that the type system gives us. Now, the first possibility I can't really do anything about. There's a team at Lightbend who is working to enhance the compiler continuously. What I'm going to try and do today is to try to give you an overview of all the features of the type system in Scala, so that you can have an idea, maybe particularly for beginners in Scala, a better idea of the things that are possible with the type system, the language it gives you for talking about types, the way you can express the types. And I'm going to try and do that in the space of an hour. We'll see how this goes. It might get intense. So, yeah, I took a decade removing some casts. And you might ask, what are the practical benefits of this? Well, I think casts are very much the enemy of refactoring. Much of the euphoria, and it was genuinely euphoria I got from Scala over the years, has come from the times where I've successfully refactored code. Rather than to carefully plan my refactoring, to decide all the places that needed changing before I changed them, I would just go and break something. I would make the change straight away without a care in the world, because I would rely on the compiler to have my back. I would rely on the compiler to tell me all the code that had broken as a result of that. And after a few iterations of fixing compile errors, and I mean, don't overlook the fact that the compiler is making my life really very trivial. It's not only telling me the problems, it's giving me line numbers as well, saying, go and look at this line in the code and fix this problem. It's a very mechanical process. It's not entirely trivial, but it makes it as easy as it possibly can be to make your code safe, make your code work again. And after a few iterations, I would maybe get the code compiling. And the most magic experience, after I'd done all of this, maybe I'd spent days, maybe literally days, without a compiling project, I would finally get it compiling, and I would run it, and it would work. And I would be so shocked, I'd be in disbelief that all this work had gone into changing the code in ridiculous ways, and the code would still work. I would start to believe that actually I was running an old version of the code, or I'd got my versions mixed up. But this genuinely happened many times in my career. And I think maybe the thing which gives me the most pleasure from writing code in Scala, this is the most, this feeling of having done a refactoring and having the compiler guide me through the process from working code to working code. This is the thing that gives me, I think, the most pleasure from writing Scala over the years. And it's kind of difficult to convey to people who haven't experienced it. But after you've had the experience a few times, after you've seen this happen, it changes you as a programmer, I think. It changes your outlook. You develop a confidence. And I like using this word confidence to describe the effect. You attempt more ambitious refactorings. You sometimes go on a refactoring spree. You change more things than you ever intended to. You see the smallest detail which is wrong, and you feel completely comfortable in changing it to whatever you think it really should be, and you rely on the compiler. This is the benefit you get from having the compiler. And I used to, well, there was this joke in the 1990s that it was impossible for adults to program a VCR, a video recorder. It had to be a child under the age of 10 who would program the video recorder to record a show on TV. It was always beyond the capabilities of any adult for some reason. And I think one reason is that there was never any real risk for the child. If the show wasn't recorded, the kid doesn't really care. They get on with their life. They still get their pocket money at the end of the week. No negative effects. If they manage to screw up totally and break the video recorder, the kid doesn't care. Their parents will buy a new one. No parent is going to get their child to give up their pocket money for a year just to buy a new video recorder. And what the Scala compiler does is it makes us all like kids again programming VCRs. We're like the kid who doesn't care if it goes wrong. We take the credit for the successes, and in the case where we don't succeed in doing whatever we want to do with the compiler, with code, with types, there's no harm done. We can walk away and try again another day. Now, this is sort of the happy story. This is when things are all working well. There are still times when a refactoring doesn't work, and we can learn from these too. I need to get this subliminal message out to you, so keep watching the screen, by the way. So there are reasons why refactorings don't work, and these teach us what kinds of code, the kind of code that is fragile under refactoring. A prime example is casts that I've mentioned several times already. Casts are this dangerous thing that is susceptible to breaking refactorings, to losing some of the safety. And it's where we said to the compiler, I know better, and the compiler said, sure, whatever, don't blame me when it all blows up. But when you refactor, when you change the code, when a string changes to an option of string, that cast will still happily compile, just as happily as it did before when it was a string. It's runtime when you experience the problem. It's runtime when you get the class cast exception. And runtime exceptions are the worst. We want to take every chance we can get to have compiler errors and not runtime exceptions. And I've taken a lot of pleasure over the years in writing libraries for Scala which make your lives harder if you are trying to write code that won't run. Adding constraints to your code which stop you compiling code which won't run. We should use types to ensure that impossible states cannot be represented in our system. And libraries like Contextual, which I released last year, makes it harder to write code that instantiates values, because it lifts what would have been a runtime parse error to a compile time error. And a library I released 2 days ago called Impromptu. This is very much a new one, which uses some quite advanced dependent typing in Scala to guarantee the evaluation order of asynchronous tasks without blocking. It uses the type system to avoid ever blocking. And I've got another library called Totalitarian, which I'm hoping to have ready in time for Scala Wave in Dansk in a couple of weeks. Totalitarian encouraged usage of total functions rather than partial functions. Partial functions can take an input which causes them to fail at runtime. Total functions will not. They are guaranteed, whatever input they take, to return a value. And all of these are trying to make it harder for you to compile code which won't run. And they work because I'm using all of the features of the Scala type system that I can. Every opportunity I get with the type system to encode this complexity, I take it, and I take advantage of it. So today, the most simple types are the same ones you would get in Java 1.4 even. These are very straightforward. They have subtyping rules, and these are simple, and we can organize them into a nice subtyping graph. So any is the top type. Top means it's higher than all the other types, that all other types are below it, and that there can be nothing higher than it. Obviously, this only makes sense if we put it at the top of a diagram. And that is an arbitrary choice, very much the same way that we decided to put north at the top and to call the top top. We could have done it the other way around, but this is how we do it, and any will always go at the top. And everything must inherit from any. All types must inherit from any, and we can prove this. So assume there is a type which does not inherit from any. If it's not a subtype, then it must either be a supertype or some unrelated type. If it's a supertype, then, well, it's higher than any, so that's a contradiction. And if it's an unrelated type, then we can get the compiler to calculate a least upper bound of that type and any. And if it's a least upper bound, then it must be a supertype of any, which is a contradiction. So by this simple thought experiment, we know that any is the unique top type of which all other types are subtypes. It's the top type because we say it is, basically. Consequently, we have a bottom type, and that is called nothing. That goes at the bottom. Bottom means it's lower than all the other types, that all other types are above it, and there can be nothing lower than it. And because it's the opposite of any, we put it at the bottom of the diagram. And that is the convention. Is everybody with me so far? One person is with me. Fantastic. Stick with it to the end. All the types in our universe fit into this diagram between the top and the bottom. And as types go, anything is more interesting than any. It's a boring type. And nothing is more interesting than nothing. And the thing about nothing is that it has no members. I can't say I've got a nothing, an instance of nothing. It's not possible, because the only way that nothing can be a return type of a method is if that method either throws an exception every single time or recurses infinitely. That is the only way you can write a method that has a return type of nothing. Now, most types in Scala are nominal. We refer to them by name. We can look them up, or the compiler can look them up by name and find out other things about them, about their structure, but we refer to them by name. It does also have structural types, structural subtypes. These exist. They are not particularly useful. So I will leave that slide there for 2 more seconds and then move on, because I don't really want to waste any time talking about structural subtyping. Types can also be made generic with either type parameters, like list A here, or with type members, like this out type in my hypothetical serializable type. And these allow us to have a type and parameterize it using some other type. It allows us to define the behavior of one type in terms of another type. At the definition site, those types are unknown. List A, we don't know what the A is, and we have to work with it as an unknown type. When we instantiate one of these, it's then that we have to specify a universally qualified type to fit into the parameter position or the member position. And these two things are kind of interchangeable. Where you use a type parameter, you could alternatively use a type member, or vice versa. And you get more or less the same functionality. There's different syntax. The syntax is more verbose in the type member case. There are other subtle differences. The syntax is also biased. I say it's biased because it's very easy to write the type serializable without specifying its type member. It's very easy for us to just forget to include those braces and the refinement on that type. Whereas for list of some type, list of string, say, we have to explicitly replace that string type with an underscore. So it feels like we're doing something wrong when we discard that additional information we have. We feel reluctant to use an underscore in places where there's a type we actually know. I did actually give a 15-minute lightning talk, which took me 45 minutes in the Northeast Scala Symposium a couple of years ago, where I explored the differences between these two in a lot of detail. So if you're thinking, well, they're not really the same, what am I talking about, then have a look at that video, and I spend a lot of time going into more detail on the differences. Okay, subtyping. Subtyping and hence supertyping. This is probably the most important type operation we have in Scala. It's the most fundamental. It comes up absolutely everywhere. We often want to ask the question, is some type A a subtype of some type B? But what does that actually mean? Well, it means if we have an instance of type A, we can always use it where a type B is expected. And this is the Liskov substitution principle, which is explained up there, and I won't read it out because it's unnecessarily complicated. It just means you can use the type B, or you can use type A where type B is expected if A is a subtype of B. And in any code, you can imagine there are lots and lots of situations where you want to use a subtype, or where you have an instance of a subtype that you want to use in position of a supertype of that. So far so good, and maybe so slow. So let's accelerate, and I'm less than halfway through, and we're going to go on to existential types. Is anyone scared? Is anyone nervous about existential types? They can be a bit scary. I don't want them to be scary. They are actually incredibly fundamental to everything we do in Scala, which is why I'm bringing them up early, because I'm going to refer back to them a number of times later. They're the counterpart to universals. Universal types are the ones that are fully known. We can give them a name. We can know all about what methods they have, what type members they have, what parameters they have. This is all known with universal types. But existentials, we maybe know something about the types, but it's less than we had before. And universals are indeed easier to work with. Existentials do make our life harder when we have to use them, and we could have used universals instead, but we don't always have that luxury. So with an existential type, we are saying we have a type, and we know that if we encounter an instance of this type, we're acknowledging that other values or types must exist somewhere for that type to make sense, or to give context to that type, but we don't know what they are. An existential type gives us a way of working with a box which contains a cat. Although we know there's a cat inside the box, there are many things we would like to do with the box that don't involve the cat. So we can make progress without knowing whether it's a dead cat or a live cat. We can still take the cat out of the box, and it's the same cat that was in the box when we started, and we can say that it was the same cat, but we don't know which of the two it was. We can... So we have to consider the situation, at least in the existential world, that the cat is both a dead cat and a live cat. So while we can take a box which we know contains a living cat, and we can feed the cat, and we can expect the cat to eat, we could also have a box which we know contains a dead cat, and we could embalm the cat. This is an operation on a dead cat. But our box, unfortunately, contains only an existential cat, so all we can do is things that work for both dead cats and live cats, for example, checking its weight. Now, my first step towards dispelling some of the complexity around existential types is to simplify the syntax for you. We've seen types written like this. Everyone familiar with types like this? Either of underscore, comma, int. The underscore is always shorthand for something like this. We introduce a type, t, but that type is existential. Either t, comma, int for some type t. We could equally say s, comma, int for some type s, and it would be the same type. Name doesn't matter. What matters is that this t parameter is existentially quantified. Likewise, if we see something like this, option of underscore subtype of exception, this is a constrained existential, and this is equivalent to this. Option of t for some type t, subtype of exception. In the existential world, when we're using this type, we can know that that t has all the methods that exception has. It may be an instance of some subtype of exception and have more methods, but all we know when in our existential world, where we have this existential option of some exception type, all we know is that it is an exception. Did you know that projection types are actually the same? Those are actually existentials too. projection types are not a fundamental part of the Scala type system. So who has seen enumeration hash value at some point? Did it make you happy? Probably not. Yeah. This is normally not what you want to see. It's annoying. So the use for hash or a pound sign is more shorthand for an existential type. This is an existential. These are completely identical types, written in different syntax. So this is an existential which says it is e.value for some type, some value e, which is unknown. We don't know what e is, but we do know that it has type enumeration. And because we know that enumeration has a type member called value, it's safe to write e.value there. So I want to try to be clear about what this means, because this is difficult. It's difficult to get your head around existentials. It took me years. So don't expect to, maybe my expectations are wrong to spend 5 minutes talking about existentials and have you all understand them by the end of it, but I'll try. This says there exists a value e of type enumeration. But the context that is usually omitted from that is to say, assuming we have somehow found ourselves in possession of an instance of this type, assuming we've got one of these, then there must have existed at some point, at its point of creation, a value e which had the type enumeration. That's quite long-winded. So we just say e.value for some val e of type enumeration. But if an instance of this type exists, then there must have at some point been an e which also existed, must have been instantiated in order to have created this type. So I would like to stress that working with existential types is harder than working with universal types. And in order to get from a universal type to an existential type, and bear in mind, we always construct universal types. They're always universal when we construct them. There's always some detail about the type, a parameter or a member. When we move into the existential world, there's a parameter or a member that is being discarded. There's some detail about the type that we lose. And when we lose it, it's normally difficult to get it back, or to get it back safely. We can make assumptions about it, but generally we are losing information. So we try as much as possible to avoid losing universally quantified types. This, for example, would be fine, though. Def length takes a list of some type, for some type t, returns an int, and the implementation is just list.size. This is completely safe because we don't care about that type parameter. To get the size, we don't need to know what the type parameter was. But this, for example, I haven't written the return type in, but the return type will be inferred to be any. We've lost the information. What we'd rather do is write def head parameter t, list of type list of t, and then we would know the return type is t as well when we get the head of that list. That would be the safe way to write this. And at the usage, at the call site, when we invoke that, the t parameter, which isn't included here, the t parameter would be whatever type of list we feed to this method. And we would get the same type out at the end. So the definition of this method is in the existential world. And at the call site, we're in the universal world. And the type t that is instantiated for when calling this expression gets transferred across the input to the output, and we don't lose it. So we're taking advantage of the existential type to transmit information, even though when we're writing the definition, we don't know exactly what it is. In the general case, this is sort of showing all the features of a existential type. We can have a path, we can have type parameters, and it can be existential on any number of types and any number of vals. Remember, what this says is there is a path of type path, which has a class member called class, and this path existed when we created an instance of type X. And type T was some known type when we created this, but in the existential world where we use this type X, we don't know exactly what those types are. We simply know that they must exist if we have an instance of this type. Now, I mentioned path-dependent types implicitly there. When they're quantified on a value, this forms part of the path to a type, commonly in the form of a series of packages separated by dots. But a type can also be dependent on the identifier of a stable value, any stable value that we have access to. And this value must be available, it must be visible, it must be in scope when we instantiate such a path-dependent type. And any instance of the class will hold a reference to it. And also, anywhere we want to refer to that type with its fully qualified path, so the path referring to the value, we need that value in scope, otherwise we can't do it. It gets raised, or we lose information and it becomes an existential. And people often don't like working with path-dependent types because it's actually very easy to lose that value, to lose the value E here, enumeration. This is why you always see enumeration hash value instead of E.value. And the way to avoid losing it is to make sure that you always pass around val E anywhere you have a reference to the type E.value. You need to pass them around together. There's no other way to keep them in scope, to keep the E in scope so that we have the context with which to refer to that path-dependent type. So I would say don't blame the compiler when this happens. The compiler, on the one hand, makes it easy for you to lose the reference to the stable path. It makes that easy. But you should be checking your code more carefully. You will find a place where you lose that type, or the association between the type and the value, and that is the place where you need to fix the code. Okay, that is the end of my existentials section and related things. Did anyone fall asleep there? Did most of you fall asleep? Did your minds wander? Hopefully, we're going to get back to something a little bit easier now, something more familiar. So I don't know how many of you here are beginners in Scala and wondering what the hell I just spent the last 10 minutes talking about when you've never experienced these existentials before. We're now going to talk about more familiar things. So let's get started with intersection types. These are written with the keyword with in Scala. For example, this one, product with serializable. It allows us to compose a new type from two or any number of previous types. And an intersection type represents a type of all the values which are instances of both the left type, product, and the right type, serializable. Everything which is both a product and a serializable has this type as well. It's a subset of all the values which are products and a subset of all the values which are serializables, and hence it is a subtype of product and a subtype of serializable. Scala also gives us singleton types. There is a singleton type corresponding to every single stable, so non-variable, value in your code. They get created on request, effectively. You can refer to we normally write it as value.type, like this. So if you have val x is hello world, we can refer to the type x.type, and we can say a new value y has the type x.type, the same type as x.type, and the only possible value that can go on the right-hand side of y is x, because nothing else has the type x.type. So what is the use in that, you might ask? It doesn't seem particularly useful. It's basically saying this is what it is, which sounds somewhat philosophical, somewhat true, but completely useless. Why would we write a method which has a parameter with a type that can only possibly take one value? We know what that value is if we can write the type. And this question brings me on to phantom types, and I will come to the answer in a second. So you may have heard about phantom types. You may have had rumors of phantom types. People may claim they saw one once. They do exist. They are real. But they're not some new structure in the type system that you need to learn. They're not like existentials or even projections. They are types you're probably already familiar with. But it's simply the way a type is used that makes it a phantom type. A phantom type will never have an instance of it. These are types which exist, we will write them in the code, but we will never have a field of that type anywhere. We will never have a parameter with the type of a phantom type. It may be a type parameter. It may be a type member. It may be a type bound. It may help to resolve an implicit, but it won't ever have instances. And it's this that makes a type a phantom type. And we can perfectly well use singleton types as phantom types. They help us to use, we can use them in various ways, for example, to resolve implicits that give a use to that singleton type. And when you're doing more and more advanced things, you will find that singleton types, phantom types become more and more useful, more and more familiar. There's no code you have to write to declare something as a phantom type. You simply just avoid ever using it in a field position. Now, you can get a long way in Scala by assuming that types are basically sets. This mental model is reasonable. Naively reasonable, I would say. We can think of the type byte as a set of integers ranging from minus 128 to 127. We can think of string as the infinite set of all possible string values. We can think of nothing as the empty set. We can think of foo.type as the set which has one value, foo. But unfortunately, the notion of types as sets does break down when you look more closely. And phantom types do highlight that, actually. What about this type? It is a subtype of both int and string. This is crazy, right? But this is a perfectly valid type in Scala. You can write this type, it won't complain. You can't create an instance, that will never be possible, because if something is an int, it is certainly not a string. But it is a subtype of both int and a subtype of string. And this is useful information, so we can use this as a bound. Using this as a bound is useful. It is not a subtype of double, it's not a subtype of exception. It is a subtype of string and a subtype of int. Now, we could use that information to resolve an implicit. An implicit type class that is covariant. I'm going to pause on that for a second. I will talk about covariance and contravariance later. You've got that to look forward to. But we could resolve an implicit of a type class of int or a type class of string using one instance which has this type if it's covariant. So that is one simple example of where a phantom type, an intersection type, which never has an instance, is useful. But it's also an example of a problem we have with the notion that types are sets. Because this has no instances and nothing has no instances. They're both empty sets, but they're not the same. This is where it breaks down. This is where we can't really continue with types and sets being the same thing. So the message is types are not equal to sets, but it can give you a little bit of an intuition as to how things work. Now, one thing we can do, we can take an intersection type. So here is foo with bar with baz. And this is something I very much like to do. It's a little pattern I've been using quite extensively for the last couple of years. We have a phantom intersection type, which allows me to represent a set of types, a set of things of arbitrary size. We can have an arbitrary number of types in our intersection. And I can test whether a type is in that intersection. I can test for set membership of one type in that intersection type using a simple subtyping check. If my set is foo with bar with baz, I can write a method called inset, and I can ask it, is foo in the set? That is fine, because I can derive the implicit evidence to say that set is a subtype of T. Is foo with bar with baz a subtype of foo? Yeah, it is. So this compiles. But is quux in the set? Well, can we get evidence that set is a subtype of quux? Quux does not appear there, so it is not. So we've used intersection types in, I think, quite a cunning way to represent a type-level set, a set of types at the type level. And this is raising more knowledge that would normally only be available at runtime to the type level. And as further evidence that intersection types work well as a model for sets, we can see that A with B is the same type as B with A. There is type equality. There are some soundness problems if you do projections on those, but we're not going to do projections, so we're all good. We can say that A with B is equal to B with A. So we have reordering, same as sets have reordering. And we can do deduplication as well. The type A with B with A is equivalent to A with B. The repetition of A doesn't matter. We deduplicate as you would with a set. If you add the same element to a set twice, the second addition is idempotent. So this gives us confidence that our model of using intersection types for representing sets at the type level is a reasonable one. And for that reason, I'm using it quite extensively, and I've found it quite fun, quite challenging at times, but also extremely useful. Now, I've spoken about intersection types. There are also union types, the categorical dual of intersection types. And although Dotty has them, Scala does not have union types. By the way, don't worry too much about me using phrases like categorical dual. I honestly don't understand it any better than you do. Probably less well in many cases. But what I will say is that you can model union types in Scala with intersection types by virtue of contravariance being the categorical dual of covariance. An intersection type in a contravariant position behaves like a union type in a covariant position. The semantics are the same. They are the dual of each other. More than that, I will not say because I will start making mistakes. But category theory gives us this, confirms this behavior, and we can use union types in Scala, even though they're not a fundamental building block of the type system. There's also another kind of singleton type in Scala, literal singletons. I'll only mention them briefly, but in the same way that a value foo gives rise to the type foo.type, the string hello world will give rise to the type hello world.type. You can't actually write this in Scala. You need type-level Scala for this type to be written in the literal sense, but all versions of Scala can actually handle the type if you have a way of producing it. So these literal types fit into the type hierarchy somewhere between singleton types and string types. The thing that they can do which value singletons can't do is that two different values can have the same literal type but different value types. So if you assign hello world to two different values, A and B, then A.type and B.type are different types. But both of these have the common supertype of the literal type hello world.type. And also the supertype string, of course. Type-level Scala also gives you access to working with singleton literals of numeric types and also symbols. So there's a lot of scope for playing around with those as well. Now, I want to talk a little bit about type conformance, which is something which I think is often confused, or often misunderstood in Scala. And this is almost the one thing I would like, the one message I would like you to remember today from this talk, which is that value conformance is not the same as type conformance. This may come as a surprise. So let me explain what I mean by conformance. To say a value conforms to a type, I'm asking, is the value an instance of the type? But to ask whether one type conforms to another is to ask, are the types the same, identical, if they're universally quantified? I'm always doing that. Or if the type is existential, if the type we're asking, do we conform to this type? If that type is existential, can we select type variables that make this type the same as this one? That is slightly different from value conformance. So if the types are universally quantified, are they the same? Or if they're existential, can we make a choice of existential type variables and values such that the types are considered the same? And whenever the compiler needs to evaluate whether two types conform, it does this calculation. It makes these choices based on a variety of factors, least upper bounds, greatest lower bounds, variance annotations, and it chooses the type variables as appropriate to check whether one type conforms to another. They're not arbitrary choices, but they are complicated, and consequently I won't talk about them. But a value, on the other hand, can have many types all at the same time. If we write val x is sum of 1, What is the type of this? Well, there's the type that gets inferred, which is sum of int. But these are all valid types for sum of 1. X.type, sum of int, option of any, option of 1.type. Obviously, that only works in type level Scala. Product, so serializable, product with serializable, any ref, any. There are others as well. X has all of these types at the same time. For X to conform to those, to a type, it can be any of these. For a type to conform to another type, it has to be equal. And you often have to think where you are using, where the association is between a type and a value and a type. And I think because we have a lot of covariant types, the behavior is very similar to value conformance with a covariant type. But we shouldn't presume that types are covariant. In the general case, they may not be. So I couldn't really give a talk on types without really mentioning kinds. And kinds are the types of types, or the shapes of types. And the compiler is kind enough. Thank you for that little, barely audible response. Thank you. The compiler is kind enough to check that the types you use are the correct kind, depending on the position you use them in. I don't know if you can see this. There is a star there. This is my shortest slide. Most of the types we work with have this kind. We call it star. These are concrete types. They can have instances. Other kinded types do not ever have instances directly. Star-kinded types can have instances. So there are things like int, like exception, or byte array output stream. And maybe you're thinking, well, what other types could there possibly be which do not have instances? So consider the type constructor list. Not list of something, but just list by itself. We call this a type constructor because we can pass another type to list, and we will get another type back. We can give an int to list, and we'll get list of int back. Maybe I even have a slide of that. No. We write this kind as star goes to star. That's one concrete type. You give it one concrete type, and it gives you a concrete type back. It's like a function at the type level. A function which takes types as its argument and types as its return values. And list is an example of one of these. But don't get confused. List of int is a concrete type. It has kind star. Option of string. These are fully applied types. We can have instances of these, so they are kinded as star. It's things like list and option themselves which have the star goes to star kind. I would say probably most users of Scala, not necessarily the audience here, but worldwide, people who are doing Scala as part of their tedious day job, they will not encounter very often any of these higher kinded types. They will only ever experience, or most of the time they will experience simple concrete types. You will see them occur occasionally, though, in one very common place, which is the to method of the collections library. Given a list of the values, a list of integers, we can convert that to a vector. Now, the to method expects a type parameter. It expects a type parameter of kind star goes to star. it doesn't expect a vector of int because it already knows we've got ints there. There's no real choice in the value type of the elements. So 2 is written in such a way that it will only allow you to provide a type that is of kind star goes to star. Okay, here we go. Covariance and contravariance. This is one of the most complicated things to get your head around in Scala. It takes years. The rules are really simple. It's just multiplying pluses and minuses. But to get any sort of intuition is something which takes lots and lots of practice. I'm not going to teach you covariance and contravariance in the next 5 minutes. They are the source of a lot of confusion, and while they are a fundamental part of the type system, I will later show you how you can write them in a simplified way, at least for the purposes of thinking about them. You wouldn't, not necessarily in terms of your code. But we probably have, you're probably familiar with types like list, which is covariant, as indicated by the plus before the type parameter t, and contravariant types like ordering, which has a minus before the t to show that it's contravariant in that type parameter. If you want a rule of thumb, the full story is more complicated, but a rule of thumb is if the type parameter appears in methods of the type as the return part of the return type, then it's probably covariant. If the parameter type t is appearing, for example, in the second line as the type of parameters, then it is probably contravariant. That is a lie, but it's a rule of thumb. The reality will take too long. The solution is, if you're not sure, pick one. Write a plus in, see if it works. The compiler will tell you if you're wrong. If you're wrong, replace it with a minus. Hopefully it'll work. If that doesn't work, you need invariance. Delete the plus and the minus. If that doesn't work, you're screwed. Yeah. I think this is one reason why it is so complicated. The easiest solution is just not care about it and make everything invariant, or let the compiler do the work for you. But it is kind of fundamental to the type system. And why is it fundamental? Well, it's all about subtyping. Subtyping, this most important operation we have when working with types. For a covariant type like list, we can say that list of exception is a subtype of list of throwable because of two facts. One is that list is covariant. The other is that exception is a subtype of throwable. The subtyping relation of the applied type mirrors the subtyping relationship of the inner types, exception and throwable. Likewise, or contrariwise, a contravariant type reverses the direction of that. So the two facts here are that ordering is contravariant and exception is a subtype of throwable, which means that ordering of throwable is a supertype of ordering of exception. They are reversed. That is what contravariance does. Now, contravariance and covariance, the plus and the minus, are definition site specifications for how those types can be considered as existentials. If we were to pretend we didn't have definition site variance, we only had use site variance, we would have to write things like this. If you wanted a list of exception, we would say list of something which is a subtype of exception. That is assuming list is in variance. Which, of course, because I told you earlier, this is the same as list of t for some type t, which is a subtype of exception. And presumably I have the opposite for ordering. Yes. If we wanted to move from definition site contravariance to use site contravariance, we would have to write this. Ordering of exception we rewrite as underscore is a supertype of exception, which means ordering t for some type t, which is a supertype of exception, such as throwable. So what we've done is we've switched from definition site variance to use site variance. We've rewritten the complex concept of variance in terms of existentials again, much as we did with projection types. We wrote them as existentials. And existential types and path-dependent types are basically the two most fundamental building blocks we have in Scala. Pretty much everything can be written in terms of those. And also projections and type applications, but a lot of the complex stuff can be rewritten in terms of existentials. So familiarity with them and being aware of when things are basically existential, this is fundamental to understanding and maybe not understanding, but reasoning about the type system. So while I've touched on a variety of concepts, I've shown that several of them can be expressed in terms of others. Projection types are a special type of existential types. Covariance and contravariance annotations are just shorthand syntax at the definition site for bounded existential types, again, at the use site. Type members and type parameters are different syntax for kind of the same thing. I'm not going to elaborate on the differences, but they're kind of the same. In Dotty, they are the same. Concepts like phantom types don't really exist. They are just the way you use the types. They're not part of the type system, especially. And we've, hopefully, by reducing all of these features to fewer, lower-level features, I've given you hope, a way to reason about the type system. And that's primarily what I wanted to do today. So what I hope it does is open up to you the richness of some of the features of the type system, giving you ways of better expressing your domains, your real-world concepts in terms of types, so that the compiler can do the work for you. And hopefully you can avoid that problematic need to cast, as I experienced at various points in my career, with less and less frequently. So hopefully this will help you to accurately model data, to model computations, so that there are fewer occasions where you're telling the compiler, I know best, and instead you can trust the compiler. You can give the compiler the information it needs for it to tell you that actually it knows best, because it normally does. And that is where I'm going to end. Thank you.